Triple integrals look like this, and what I mostly want to show you in this PowerPoint is how we describe the region that we're integrating over. We'll first be considering functions of x, y, and z, 3 dimensions, and we'll start much like we did in double integrals by considering regions where we have constant limits on the x, the y, and the z. And that three-dimensional region would look like a box or a cube, actually a rectangular solid. Cube would imply that they're all the same dimensions, and they're not. Now, if the limits on the x, y, and z are constants, in other words, if we're integrating over a boxed region, we can integrate in any number of orders. Here are the 6 different orders of integration. We just want to make sure that we have things matched up. You can see in my terminology the x is going from a to b. Well, in this first integral, the x is the first variable of integration, and it's going from a to b. In the second integral, the x is the first variable of integration, and it's going from a to b. In the integral on the bottom left here, x is the second variable of integration, and it's going a to b. So again, as long as we get them in the right positions, we can integrate in any of those orders and not have to spend a lot of effort figuring out what the order of our integration needs to be. So since we have rectangular regions described here, we can do our integral in any order that we want. So if we integrate first with respect to z, then the z would go from 0 to 1. If we integrate then with respect to y, that would go from 1 to 2. If we integrate then with respect to x, that would go from 2 to 3. Now, this can be done by the same property that we studied for double integrals. We have a function of x, we have a function of y, we have a function of z, all multiplied together. So we could split this into separate integrals. We can do the integral of the x, the integral of the y, and the integral of the z independently and multiply them together. And we can do each of those by hand. Of course, we could type this integral into our TI-89. Much quicker. So then what do we do if we're integrating over a region that is not a rectangular solid? So here's the three-dimensional counterpart of what we talked about for double integrals. We have our region, which is a three-dimensional solid. In this example, you can see that any line drawn parallel to the z-axis that's passing through that region is going to go from one surface described as u1 parentheses x comma y to the other surface described as u2 parentheses x comma y. Here we would have an integral where our first variable of integration would be the z. So if this is z simple, if we can pass a line parallel to the z-axis that goes through the region in two distinct surfaces, then we would start with z as our first variable of integration. Then we would worry about describing the remaining region. In this example, we're going to be integrating the function 2x which is really of no significance to us. What we're really interested in is describing the region Q. So Q, it says, is the solid in the first octant above the disk x squared plus y squared equals 9, and below the plane x plus y plus z equals 6. So we're going to take out our maple and see if we can't get an idea of what that's talking about. Now here's a graph of the three-dimensional region. I've color-coded each of the surfaces so we can distinguish them. Let me show you first off. Here is position where we can see the y-axis. Here's the y-axis, and if we make lines parallel to the y-axis, you can see up in here a line that's parallel to the y-axis is going to go through this green surface and this red surface. Down here, however, a line parallel to the y-axis is going to go through the green surface and the gold surface. So this is not y-simple because it doesn't go from one surface to another all the time. So let's twist this around. Here we're looking at a position where we see that there are the x-axis here, a line parallel to the x-axis would enter the solid here and exit through the gold surface. But here, a line parallel to the x-axis would enter here and exit through the red surface. So again, we do not go from the same surface to the same surface. And if we take a look at a different position, so in this position we see the z-axis here, a line parallel to the z-axis would enter this blue surface and exit on the red surface. And that would happen anywhere for that figure. Looking at it straight down the z-axis, from this direction all you see is blue. From this direction all you see is red. So again, parallel to the z-axis, you're always going from blue to red. So one surface to the other makes it z-simple. So now that we know that it's z-simple, z will be our first variable of integration, we need to establish what are the two surfaces that we're going from and to. Well, we were told that it was above the xy plane, that's here, and below the plane x plus y plus z equals 6. Well, that's this plane. We've just rewritten it as z equals, so that when we write our integral, we can say z is going from bottom to top. Now what remains is for us to describe the area that is the projection onto the xy plane. So we need to describe this area in terms of x's and y's. And I'll show you what that looks like. So I've taken that graph and I've tilted it so that we are looking straight down the z-axis, and here's the image we see, the projection onto the xy plane. Now we've got to describe this region. And so here I've drawn another graph of this. You can see that this region, x squared plus y squared equals 9, is a quarter of a circle with a radius of 3. Well, if you take the x squared plus y squared equals 9 and solve that, you get y equals the square root of 9 minus x squared. So we could describe that in terms of x's and y's. And so the integral of this region, we could imagine our vertical rectangles, type 1 region, and we're going from the y value on bottom is 0 to the y value on top, which was the square root of 9 minus x squared. And then finally, for that region, the x's are going from 0 to 3. So that's how we set up the integral. Now, having already established the first variable of integration, needing to describe this region, we could describe it in polar coordinates. Now, the region we see here in polar coordinates, if we remember, polar coordinates have to have the r and then the dr. R would be going from 0 to 3, and the d theta, well, the theta that represents this quarter of a circle would just be 0 to pi over 2. And once again, the mechanics for evaluating this are to start on the innermost integral. Well, we're integrating first with respect to z, so since this doesn't even contain any z's, we would just copy that down and stick a z on it. And then we'll substitute for the z, the 6 minus x minus y, and the 0, and subtract. Then the next level of integration would be the polar integration. Well, to change this to polar coordinates, we need to replace the x's and the y's with r cosine theta and r sine theta and simplify some. And then we'll integrate that with respect to r. Substituting 3 and 0. And then integrating that with respect to theta. The first one, the second one, and the third one. And of course we could have typed all that onto our calculator. Now to type this on the 89, where we convert the second two integrals to polars, you can see here we need to tell it to do that integral, but then we use the with character and give it our polar conversions. So let's take a look at this, which would be an x simple region. That means when we set up our integral, we will be first integrating with respect to x. Then we need to describe the remaining projection of that image onto the YZ plane. So in this example, we're trying to find the volume, which means we'll just be integrating the function 1. So it's basically the region we're integrating over that we're interested in. So we want the part that's in the first octant again, bounded by the plane, the YZ plane, and the cylindrical surfaces given here. Now I've used Maple to construct a few images. However, that's still not enough for me to know exactly how to go about integrating this. So let's take a look at the region in Maple. Now here's the graph of the region with each surface color coded so we can distinguish the different sides of the figure. And so we want to take a look first off at maybe the y-axis, since that's the one facing us. I'm going to go ahead and not draw the lines on this like I did earlier and just show you. Here I'm looking at the y-axis. I'll just show you the y-axis. So I'm looking at the y-axis and I want to look down from both directions on the y-axis. So I'm simply going to tilt this graph. You can see we're looking down the positive end of the y-axis. Now look at what we see. We see two different surfaces. That means if we're drawing a line which goes straight away from us, I'm going to represent that with a dot. There would be a line here that would enter through the green surface. There would be a line here that would enter through the red surface. Looking at the other end of the y-axis, we see only the gold surface. So we'll have some lines that go from the gold surface to the green surface, and some lines that go from the gold surface to the red surface. That is not y-simple. Let's do the same thing with the z-axis. Now here we're looking sideways at the z-axis. Let's look down from the positive end of the z-axis. Here we are looking down the z-axis, and what do we see? Two different surfaces. Looking down from the negative end of the z-axis, we see one surface. So again, any line drawn parallel to the z-axis will enter through the green surface and exit through sometimes the gold, sometimes the red. That is not z-simple. What makes it x-simple is if we look down the x-axis. Here we are looking down the positive x-axis from the positive direction, and we see only the red. We look from the negative direction on the x-axis, we see only blue. Every line parallel to the x-axis would enter blue, exit red. That is x-simple. So having identified the two surfaces that make it x-simple, we need to describe those as x equals. So there's the YZ plane we were talking about, and there's the other plane that we were talking about. So our integral then is going to start with the dx and go from 0 to 8 minus y minus z. Then, of course, we need to describe the rest of it, and we need to look at the projection onto the YZ plane in order to do that. So I've taken the graph from Maple and twisted it around so that we're looking down the x-axis at the YZ plane. So here's what we see in the YZ plane, and we need to describe that. So there's one line, and there's another line. So that's the region that we're trying to describe. Well, having described the two boundaries in terms of z equals something, it makes sense that our next variable of integration should be the z. And so we want z to go from 3y over 4 to 3 root y over 2. And finally, the y's would have to go from 0 to 4. And I'll just show you the evaluation of this integral without detailed explanations. So finally, a region that is y-simple would be one where we pass lines parallel through the y-axis through the region and they contact two distinct surfaces. And again, that just indicates that we'd be integrating with respect to y first and then describing the remaining region in terms of its projection onto the xz plane. So in this example, we're going to be evaluating this integral, and the region is described as a region that's bounded by this surface and the plane y equals 8. So like before, we'll draw that off and have a look at it. Here's a graph of the region we're trying to create the triple integral for. So let's have a look at each direction. For example, here we're looking sideways onto the z-axis. Let's look down the z-axis from both directions. Here we are looking down the z-axis from the positive direction. Here we are looking down the z-axis from the negative direction. What do we notice about that? Well, it's blue both ways. I mean, look at the figure. You're going from blue to blue. You're going from one surface to the same surface. You're not going between two different surfaces. That is not z-simple. Well, it looks the same in the x direction. Here we're looking sideways onto the x-axis. I will twist it so we're looking down from the positive x-axis, blue. We're looking from the negative x-axis, blue. So from both directions on the x-axis, we can see we would be going from one side of this surface to the other side of this surface. That is not two different functions, so it is not x-simple. How about y-simple? We'll twist it so that we're looking down the y-axis. Here we are looking down from the positive y-axis. We see all red. Here we are looking from the negative y-axis, and we see all blue. Any line drawn parallel to the y-axis is going to go through blue and red. Two distinct surfaces. That's why it's y-simple. Now, having established that this is y-simple, we need to describe the two surfaces in terms of y equals. Well, they already were described as y equals. That was also a pretty good hint that it was going to be y-simple. And so here, our first variable of integration would be the y. Then we need to describe the region, that's the projection onto the xz plane. Now here's the image that we see looking down the y-axis onto the xz plane. Now that's a circle with a radius of 2. That generally indicates that we could convert the remaining portion into polar coordinates. And so in this example, I'll go ahead and perform this first integral that we've already set up. Then we'll worry about the remaining two integrals. And so here's the integral. And we will now convert that integral and the region into polar coordinates. So I'm going to go ahead and convert the function first into polar coordinates, then worry about the region. And so just remembering that we got x and z and not xy, that is x equals r cosine and z equals r sine, and x squared plus z squared equals r squared. So if we substitute those and simplify, now to describe our region in polar coordinates, we notice simply that r is going to be going from 0 to 2, and then theta is going to be going from 0 to 2 pi. And then we just need to evaluate that integral. And I'll finish out the evaluation without making you listen to me do it.